In this lesson, we're answering the question, how do you solve an equation when the variable is under a radical symbol? Now, in the warm-up, you took radical expressions and raised them to powers to solve a linear equation. In this part of the lesson, we're going to be focusing on the inverse operations that you're already familiar with to solve equations, like taking an addition problem and using subtraction to solve it, or solving a multiplication problem with division, solving a radical problem using exponents. Now, in this next part, you're going to be combining these concepts, and you're going to be working with roots other than square roots. Let's take a look at radical equations. Now, radical equation is an equation that contains at least one radical with one or more variables in the radicand. Here's some examples. Here I have a radical, cube root, and I see that one of the variables is inside. Same thing here. Here's a square root with a variable inside. So even though I have a variable outside, it's still an example of a radical equation. These are examples of non-radical equations because even though I have radicals, notice the variable is not in the radicand, which means that these equations can be solved using properties of addition, properties of multiplication. Now let's take a look at solving a radical equation. I have x equals the square root of 9x plus 18 minus 2. I can't get my x's together because I have one inside the radical and one outside the radical. So what I need to do is to isolate the radical first so we can get rid of it. So I'm going to add 2 to both sides. It gives me x plus 2 is equal to the square root of 9x plus 18. And now I can get rid of that radical by raising each side of the equation to the same power. So I'm going to square both sides. Now squaring x plus 2 is x plus 2 times itself. So I end up with x squared plus 4x plus 4. And the square root just gets rid of the square root, leaving it 9x plus 18. Now, let's solve it. I have a quadratic, so I'm going to subtract 9x from both sides. And I'm going to subtract 18 from both sides. That's going to give me x squared minus 5x minus 14 equals 0. That's factorable to x minus 7 times x plus 2. Setting each one of these factors equal to 0, I'm going to end up with an x value of 7 and an x value of negative 2, but we still need to check our final answer. So, I have x equals 7 and x equals negative 2. Let's check x equals 7. 7 is equal to the square root of 9 times 7, which is 63, plus 18, all minus 2. Well, 63 plus 18 is 81. The square root of 81 is just equal to 9, so I have 7 equals 9 minus 2. 7 equals 7. That's a true statement. What about x equals negative 2? Negative 2 is equal to the square root of 9 times negative 2, or negative 18, plus 18 minus 2. Negative 18 plus 18, that's just 0. So I end up with the square root of 0 minus 2. Well, the square root of 0 is 0. So 0 minus 2, negative 2. And we see that that works out. So we can solve a radical equation by isolating the radical, get rid of the radical by raising both sides of the equation to the same power, and then just solve our equation that remains. So let's talk about extraneous solutions. Now, an extraneous solution is a value that arises from the algebraic method of solving, but it's not a solution to the original equation. Why would this happen? Well, look at this example. I'm solving and checking the square root of 3x equal to x minus 6. Now, I know that 3x, the value of the radical, has to be positive, because you can't take the square root of a negative number. But notice that, depending on the value of x, if I ended up with a solution that's less than 6, by subtracting 6, this expression on the right is going to be negative, which wouldn't work. You can't take the square root of a number to get a negative result. So we always have to check our answers to see if it works in the original equation. Now, in solving this, I'm going to go ahead and square both sides to get rid of the radical on the left. So by squaring the square root of 3x, we get 3x. On the right side, I'm squaring the binomial of x minus 6. So I'm going to take x minus 6 times x minus 6. And by using the distributive property, I end up with x squared minus 12x plus 36. Seeing that I'm dealing with a quadratic, I'm going to go ahead and subtract 3x from both sides to get it equal to, on the left side equal to 0. And the right side, I'll have x squared minus 15x plus 36. Now, this expression is factorable, so I'm going to solve using the zero product property. Factors of positive 36, that I get negative 15, or negative 12, and a negative product property, I'm going to set each factor equal to 0. So x minus 12 equals 0. And adding 12 to both sides, I get x equals 12. There's one solution. And then for x minus 3, once I set that equal to 0 and add 3 to both sides, I end up with x equal to 3. Well, let's start with x equal to 12 and we check. To check this, I'm just going to substitute 12 in for x in the original equation. So I have the square root of 3 times 12 is equal to 12 minus 6. Let's simplify. Well, 3 times 12 is 36. So I get the square root of 36 is equal to 12 minus 6, which is 6. Well, the square root of 36 is 6. So 6 equals 6, so it checks out. Alright. Let's do it again, only this time we're going to substitute in 3 for x. Now notice that the value of x is less than 6, like I was talking about before. And since it's less than 6, by plugging in 3 on the right side, I'm going to end up with an expression that's negative 3. Well, 3 times 3 is 9, and the square root of 9 is equal to a positive 3, but 3 does not equal a negative 3. This does not check out. This is an extraneous solution, so let's put that in here. The value of x equals 3 is extraneous. It was an extra solution that arose. Even though I solved this correctly algebraically, I ended up with a solution that didn't match the original equation. So, the only solution to this equation is x equals 12. Let's take a look at real world connection involving wind velocity in a hurricane. A mean sustained wind velocity represented by the variable v can be determined by the equation v equals 6.3 times the square root of 1013 minus v. V represents the air pressure in millibars at the center of the hurricane. So what's the approximate air pressure? So we're looking for v. At the center of a hurricane, the mean sustained wind velocity v is equal to 48.6 meters per second. So let's plug that into our formula. So I have 48.6 is equal to 6.3 times the square root of 1013 minus p. As I go through this solving, we're going to end up with decimal values that we have to round on the screen. But keep in mind, you don't want to round any of these values until the very end. So use the exact values as much as possible. First thing I'm going to do is I'm going to divide both sides by 6.3 and isolate the value. Now 48.6 divided by 6.3 is approximately 7.71. So remember, just the approximate answer, 7.71, is equal to the square root of 1013 minus p. So now I'm going to go ahead and square both sides to get rid of the radical. So on the left side, I'm coming up with a value that's about 59.5. So I'm just going to write approximately 58.5. And on the right side, the value is gone. So I'm left with 1013 minus p. Now I'm going to go ahead and p isolated by first subtracting 1013 from both sides. So on the right side of the equation, I still have a negative p. And on the left side, by subtracting 1013, I'm going to get a value that's approximately negative 953.49. So it's all meant for p. The only thing left out in the p is divided by negative 1. So we need to put a p value. It's positive. And if you take a negative 953.4 million divided by negative 1, you're going to end up with a positive 953.4 million. Keep in mind, I said these are all approximate values, so let's put our approximate sign here. It's approximately 953.49. And what was our air pressure? We had it was measured in millibars, so 3 millibars. So given a wind velocity of 48.6 meters per second, we get the air pressure at the center of the hurricane would be approximately 953.4 million millibars. In this lesson, we're continuing to answer the question, how do you solve an equation with a variable is under a radical symbol? And So far, we've been solving radical equations in which we were presented with a radical equation and the variable was inside the radicand. Now, we're going to be taking a look at radical equations, only this time we're looking at equations that are in exponential form. Now, an equation that's in exponential form is actually just a radical equation in disguise. So we can still use that equation, write it as a radical equation, and then solve it using the same steps as before. So let's take a look at this. Let's take a look at equations containing rational exponents. Now I have the quantity x minus 5 raised to the 2/3 power is equal to 4. Let's see what it would look like as a rational or radical equation. Well, the cube on here, the 3 is actually a cube root because it's in the denominator, so it's actually the cube root of the quantity x minus 5 quantity squared. In order to isolate, now that this is isolated, in order to solve, I'm going to cube both sides of the equation. Now, cubing both sides of the equation, raising it to the 3rd power, would only get rid of the radical. But notice I still need to get rid of the exponent 2. We can get rid of the square with the square root in terms of exponents. Let's put in 2 in the denominator for the index. So we get 3 over 2. So what I'm actually doing to solve this equation is just raising both sides to the 3/2 power. Well, if I come back over here and look at my equation, x minus 5 raised to the 2/3 power equal to 4, think about what raising to the 3/2 power would do. Well, if I raise this to the 3/2 power and this side to the 3/2 power as well, look at the exponents. When I'm taking an exponent to another exponent, we multiply. 2/3 times 3/2 is equal to 1 because I'm multiplying by reciprocals. So I'd be left with just x minus 5. So when we're dealing with rational exponents, we just need to multiply or take both sides to the reciprocal of that exponent. So 2/3, we took it to the 3/2 power. On the right side, I have 4 to the 3/2, but 2 is the square root. So we take the square root of 4 first to get 2, leaving just 2 cubed. And then we're left with x minus 5 is equal to 8. But I'm forgetting something. Remember the rule, the nth root of x to the n is equal to x. But if n is even, we use the absolute value of x. And notice that we took the square root because the index was 2 when I was looking at it in radical form. So, since I took the 3/2 power of both sides, you can look at the numerator in the original equation, the numerator of the rational exponent in the original equation. If it's even, then you know you're going to be following this rule. Therefore, we need to apply the absolute value in this case. So the absolute value of x minus 5 is equal to 8. Well, that leaves us with 2 equations. We have x minus 5 is equal to 8, or x minus 5 is equal to negative 8. We're solving both of those by adding 5 to both sides. I'm going to get x is equal to 13, or x is equal to negative 3. And of course, we still need to check our final answer. So let's go back to the original equation and check. I have x minus 5 to the 2/3 power equal to 4. Starting with x equals 13, I'm going to get 13 minus 5 raised to the 2/3 power equal to 4. 13 minus 5 is 8. 8 to the 2/3 power should equal 4. Well, the cube root of 8 is 2, so I'm left with 2 squared equal to 4. And if you square 2, you will get 4. So we see that that's a true statement. Now let's look at x equals a negative 3. And negative 3 minus 5 taken to the 2/3 power should equal 4. Well, if I take the negative 3 minus 5, I'm going to get a negative 8. To the 2/3 power is equal to 4. The cube root of a negative 8 is a negative 2. So I'm ending up with a negative 2 quantity squared is equal to 4. And if you take a negative 2 and multiply by itself, you will get a positive 4. So that checks out as well. So when looking at equations containing rational exponents, using the rule of when it's in radical form, we can end up seeing that just by raising both sides to the reciprocal of the rational exponent, we can use it to solve for the variable. Let's take a look at a real-world connection. We're going to involve astronomical science. In this case, Kepler's third law. Now, Kepler's third law states that P is equal to A to the 3 times power. P represents the time it takes for a planet to make one revolution around the sun in years. Now, A represents the planet's distance from the sun in astronomical units, and it uses Earth as a reference because Earth takes 1 year to move around the sun. So by plugging that into the formula, well, 1 to the 3 halves power is equal to 1. So we know that Earth is 1 astronomical unit away from the sun. We're going to be taking a look at Jupiter. If the orbital period of Jupiter is 11.9 years, then what's its distance from the sun? To the nearest hundredth of an astronomical unit. So we can plug in 11.9 for P. So we have 11.9 is equal to A to the 3 halves power. Now, since I have a variable raised to a rational exponent, I'm going to go ahead and raise both sides to the reciprocal of my exponent 2/3. And by raising A to the 3 halves to the 2/3, well, then we are going to end up with a value of just A. So I'm left with 11.9 raised to the 2/3 power. Now, raising 11.9 to the 2/3 power, we can square it and then take the cube root, or take the cube root and then square it. It doesn't really matter which one we do. If we squared it first, we get approximately 141.61, and then we would take the cube root of that and get a value of 5.21. Now, it's very important that we don't round our answer until the very end to avoid making any rounding errors. So, rounding to the nearest hundredth of an astronomical unit, we end up with a value of 5.21 equal to A. So, we're dealing with 5.21 astronomical units. What does that mean? Well, if 1 astronomical unit is the distance from the Earth to the Sun, then the distance from Jupiter to the Sun is more than five times the distance from the Earth to the Sun plus a little bit